All right. So this is section 10A. We're talking about the normal distribution. So for a normally distributed random variable x with mean of mu and standard deviation of sigma, we write it like this. This implies a normal distribution. All right, so that's going to be your mu. In other words, the population mean, and this is sigma squared. Which is the same thing as variance. Remember, standard deviation is actually the square root of the variance. So that would actually be your variance. Here's what it looks like. It looks like a bell curve, is what it looks like. It looks like a bell curve. The center of that curve, first of all, it is symmetrical. And the center, that line of symmetry, is going to be your mean. So the mean is at the very center. And then the width of it, now I use width in quotation marks because technically it's infinitely long. I mean, this thing, think of there as being an asymptote. Okay, it's going to get closer and closer to this axis, but it's never going to touch it. There's always a chance that some crazy event can occur as far out as you could possibly imagine. It's probably not going to happen. That's why it's so teeny, teeny, tiny small. So when I say width, I'm talking about like kind of like the overall shape. It could be very skinny like this. It could be very wide. It could be like this. Kind of get covered up there. So I mean, so this, it all depends on what is that standard deviation. Whatever your standard deviation is, that tells you what kind of roughly how wide that curve is. All right. So the area under the curve corresponds to the probability of x taking the values in that interval. So that's how you know what the probability of it occurring is. And so let me just kind of move this down further so you can get a better idea. Let me see if I can't move this picture. Maybe I can just move it over here. There we go. I mean, there's nothing over here. That'd be fine. Okay. Let me move it just a little bit more. All right. Now I think I got the whole thing in here. Okay, so let me show you what I mean by area under the curve. So what's the probability of some random event taking a value that's between the mean and then the mean minus one standard deviation? All right, so again, the sigma is the standard deviation. So between the mean and the mean minus one standard deviation, what is that probability? The probability that the value falls in here is going to be 34.13%. So in terms of area under the curve, like this entire area, if I added the entire area under the curve, it would give you exactly 1. And if you look at the formula, and I said FYI, you don't have to know this formula, okay? We have to get into integral calculus just to make sense of why it's set up the way that it is. But just so that you know, it's not completely made up. I mean, there is an actual function. This is called a probability density function. And that's where this all comes from. So if I looked at the area under this curve right here, it will add up to exactly 1. And so just make sure you write this down. So you do need to know these values. Okay, you need to know all these values. And then I can also say that 68.26% of the values lie between your mu minus sigma and mu plus sigma. So in other words, anything between -1 standard deviation and +1 standard deviation. All right, between those standard deviations, I can say that 68.26% of the values are going to fall in that range. What if I make my range bigger? Okay, I go 2 standard deviations to the left and to the right. So if I go 2 standard deviations to the left and to the right, I'm talking about from here all the way to over here. Notice that's a pretty good chunk of that curve. In fact, it is 95.44%. So there's a 95.44% that your random variable is going to lie within this curve. Or your, how should I say that? Your event is going to lie within this curve. The event that a variable takes on a value between here and here, it's going to be 95.44%. And then finally, if I take it out even further with 3 standard deviations to the left and 3 standard deviations to the right, then I cover up 99.74% of the values. So 99.74% of my expected values are going to lie in this region right here. And then finally, copy example 1 on page 303. I think with that one, you should be good on that and the homework as well. Let me just kind of pull it up. And this kind of gives you a more down to earth kind of look at how we actually use this. So when I talk about random variable, I mean, what do I mean? Well, like in this one right here, we're talking about chest measurements. What's the probability of a chest measurement being between 87 centimeters and 103 centimeters? All right. So that's kind of the real world interpretation of it.